Okay, so far we have talked about the definition of a limit and the fact that a limit might not exist. Another possibility is that the limit can actually be equal to infinity. Now, infinity is not a number, and we shouldn't treat it like a number because some funky things go on. So just be careful with that, but it is the case that a limit can be equal to infinity. Okay, so here I have the graph of the function y equals 1 over x squared. So it has this vertical asymptote at 0, which you can see from the graph. And as x approaches 0, the values of the function, we might say they increase without bound, or they approach, the values of the function increase without bound. So meaning they just keep on getting bigger and bigger and bigger. Or you could say y approaches to be consistent, or the values of the function approach infinity, right? So that is the idea of approaching infinity, is that it just keeps increasing without bound, so it just keeps getting bigger and bigger. Okay, so we would write in this case that the limit as x goes to 0 of this function, so 1 over x squared, is equal to infinity. Okay, one more thing about writing this with limit notation. Now, I wouldn't want to write the limit, so let me write this in red. So I wouldn't want to write the limit as x goes to 0 of y, even though I've written over here that y equals 1 over x squared, because it's not clear that y depends on x, and so is this just a constant, or is it a function? That's not so clear, so I want you to either write something like the limit as x goes to 0 of an expression in x, or of a function, so f of x, where the x actually appears there, and maybe you could define the function elsewhere, right? Okay. Okay, so this limit is actually equal to infinity. And notice that, so we do need to have that both sides, when we're approaching from either side, it goes off to infinity, right? So that is the case here. So we can say that the limit is equal to infinity. Now we have a different, because this is a little bit different of a situation, we have the intuitive definition of an infinite limit. So this is going to be similar to our intuitive definition of a limit. So the limit as x approaches a, let me just put it, the limit as x approaches a of f is infinity if the values of f can be made arbitrarily large by taking x sufficiently close to a. So the reason why I'm saying here that this is called the intuitive definition of a limit is that there is a very formal definition of a limit. We're not going to be covering it in this class, but there's a way of making all of this completely mathematically sound, and unfortunately it's not that intuitive, which is the reason why we have this version. Okay. So that is the definition, and just to have this down, something that you should remember is that infinity is not a number, and you shouldn't treat it like one. For instance, infinity minus infinity is not well defined. So we can't even do basic arithmetic with infinity. So it's definitely not just a regular number. Okay, so now let's do an example. So here we're given the graph of a function g, and we just want to find the following limits. So the first one is the limit as x approaches 3 of g. And so if we look at the graph, see that it's sort of approaching 1 if we approach from the left, but it's approaching 4 if we approach from the right. So that means that this limit does not exist because we get those conflicting values. Okay, and then as we approach 1, well, the function is nice and continuous there, so it's actually just going to be equal to the value of the function, so 5. And then at 5, if we approach from the left and the right, we will be approaching the value 6. And even though the function is not defined there, the value of the limit is equal to 6. Okay. So there is a notion of one-sided limits. So we've seen a couple, or at least 2 examples of this, where we get 2 different values depending on which way we approach the number. So we have a way of talking about that, and that is the one-sided limit. Okay, so we refer to these as the left-handed and right-handed limits. So the left-handed limit means you're going to approach the point from the left, only the left. Let me write this a little bit nicer. Okay. Okay, so with a left-handed limit, we only approach from the left-hand side of A. It's the left-handed limit. And the notation for that, it's very similar to our regular limit notation. So this is as x approaches A, but in order to denote that we're only approaching from the left-hand side, we put a little minus sign. So you can think of this as being like in the exponent of A, although it's not actually an exponent. It's just a minus, right? Of f of x is equal to L. Okay, so that would be the notation. Jeez. Okay, and then similarly, we can approach from the right-hand side. So the right-handed limit is where we only approach from the right. Of A. And then in that case, the notation is similar, but we have a plus right there instead of a minus. Okay, so those are the 2 types of limits. So those are the only ways we could approach. It's either from the left or the right, or from both sides. Okay, so one thing to remember this notation, like whether the minus means left or right. So to remember the notation I think it's helpful to think of just the number line and imagine you're standing at 0 and then all of the negative numbers are to your left, right? And all of the positive numbers are to your right. So we get that minus sign to denote the left-hand limit because the negative numbers are to the left and positive numbers are to the right. Okay, so I think that that's helpful for remembering that. Okay, so let's look at this example. This is the same function that we've been talking about from the first page. And in this case, we already mentioned this before, so let's just use our new notation to write this down. So if we were to approach 2 from the left, so we have our little minus here of this function. I think it is g. So if we were to approach from the left, we get minus 1. So that is the left-handed limit. And then the right-handed limit of this function is 1, right? And just to reiterate, so the full limit, or you could call it the two-sided limit, this does not exist, as we mentioned before. Right? Okay. Okay, so one thing about, so the relationship between these one-sided limits and the regular limit is that the limit as x approaches a, so x goes to a, of f is L if and only if, so this is a very strong statement, so this is if and only if the left and right hand limits right-handed limits are, if they both agree and they're both equal to L. So, well, that means the same thing. So the regular limit is equal to L if both the left and right hand limits are equal to L. Okay, so in math, how we would write this is that the limit as x approaches a of f is equal to L, if and only if, that's what this symbol means. So if and only if we get that both of these, so right hand limit equals L and left hand limit equals L. And when we write down that is equal to L, that means L is a number, and so both of these limits must exist as well. So we can't get does not exist for one of them and L for the other and say that the whole limit is equal to L, right? Okay, so we have another example where we are also finding the left and right hand limits from the graph. So in this case, we'll start with the left hand limit as x approaches 2. So if we're approaching 2 from this side, the value of the function approaches 3. And then if we're approaching from the other side, so the right hand side, then the value of the function approaches 1, right? And so since these are different by what we wrote up here, that means that the full limit is, well, it does not exist, right? Oh, geez. Okay. And now in the second, now we're looking at approaching 5. And so as x approaches 5 from the left, the function approaches, it looks like 2. So we would get that the limit is 2. And the same thing if we approach from the right. So we would also get 2. And since those both exist and are equal, that means the full limit exists and it's equal to 2. Okay, so there was a lot of information, but actually applying it shouldn't be too bad, I think, just from looking at the graphs. And of course, we'll get more practice in class. So just make sure you fill out the comprehension check question before class. Okay, bye.